So in part one, we took a look at the Rode NT1, and the circuit I've discovered is extremely familiar if you've looked at the TLM103. The two circuits are nearly identical. So this is an $1,100 microphone. The Rode NT1, I think, is a $300 microphone, something like that. This one seems to have better construction, though. Let's take a look at the PC board inside. So the PC board is not a FR4 fiberglass board. It is actually a hard alumina board, like a ceramic board. And one reason to do that would be to have very, very low leakage. It also seems to be covered in some type of material that probably reduces the leakage as well, some type of conformal coating. But the really interesting thing of this board is that it's not just a surface mount board. While there are some surface mount components, some of the resistors are actually deposited directly on the alumina substrate. You can kind of see those as black rectangles. So it's interesting that some of the components, all of the resistors, were done, well, not all the resistors, but most of the resistors were done with this deposition on the PC board, and they were laser trimmed. And so the accuracy of all of these resistors are very good. Now, I don't know if the laser trimming is done just to hit a particular value, or once the product is actually built, then it goes under a test, and it's laser trimmed while under test. That's my guess, is they probably try to squeak everything out of this thing, so they probably look at some parameters and laser trim the devices to match whatever components were put on the board. Now, I said most of the resistors. The 1 gigohm resistors are actually surface mount parts, and there are 2 of those, I believe. Yeah, 2 of those. Now, this side of the PC board is all of the amplifier. The back side of the board is a different circuit. The back side of the board is all the power supply circuitry. So it has the Schmitt trigger inverter package to do the DC to DC conversion. It has the Zener diodes and all those types of things. It has the charge pump, gives you 60 volts, something like that. So one side of the board is amplifier, one side of the board is DC to DC converter. So the only schematic that I found was a hand-drawn one by this fellow quite a while ago now. But let's take a look at this circuit. The first circuit we're going to look at is the bottom side of the board, the power supply side. So power comes in on pins 1 and 2 as phantom power. They go through a capacitor, and then the first thing they do is they encounter a 15 volt Zener diode. So the first 15 volts of the 48 volts coming in is stripped off, and that 15 volts goes to the 74C14, the Schmitt trigger inverter. The Rode part used a 4106, I believe. It's basically the same part. So this does the DC to DC conversion. I think the Rode part claimed to get to 73 volts. This one claims to get to 60 volts. I kind of believe the 60 volt number, but and they're going to use minus 60 volts, not plus 60 volts, but minus 60 volts. So the next part of the circuit we'll take a look at is at the bottom here. It's a buffered Zener diode. There's a Zener diode that creates a voltage, and that voltage is 13.8 volts. So 13.8 volts goes up to the top side of the board to do all of the amplification, and the minus 60 goes to the capsule display biasing. Now there's a very interesting circuit between these two sections, and this is a current source, and it's a JFET current source. And the reason it's in there, and it's a very interesting way they have it set up too. It has a T network, an RCR resistor, capacitor, resistor network going into the gate. And that must be to filter out any noise, try to keep this thing as quiet as possible. So what it does is it creates a current source, but its main job is to buffer that top section, the DC to DC converter, which is probably very noisy, from the bottom section. So it keeps those two apart, keeps any noise from passing from top to bottom. That's the circuit that the Rode amplifier did not have. So I believe that the power supply section of this product is better than the Rode. Here's a look at the DC to DC converter. It's very similar to the one Rode had. A little bit different in architecture, but not much. Okay, let's go to the top side of the board. The top side of the board has the amplifier. The place we'll start is at the very, very right-hand side of this schematic, and this is where the connection to the outside world is. 1, 2, and 3 is the XLR connector. 1 is ground, 2 is plus, and 3 is minus. Much like the Rode, there is no minus. It's just reference to ground, but a capacitor is used, and in this case also a resistor. I don't remember if the Rode had a resistor or not, but that's to keep the impedance between the plus and the minus exactly the same. So it is a differential pair that goes out, even though one side just goes to ground. If there's any common mode noise, it will appear on both pins and it will see it equal impedance. All right, if we move over, we will encounter a circuit that we should be very, very familiar with. This is the op-amp circuit. This is the push-pull amplifier with the diode biasing for a Class AB amplifier, and the PNP drive transistor at the top, and a current source at the bottom that's exactly the current source that we saw in my op-amp tutorial. So this looks very, very familiar. All right, if we go over to where the JFET is, we'll notice that there are 2 JFETs, not just one. And this is a very special circuit. And this is very different than what the Rode amplifier had. The Rode amplifier did some tricks with bootstrapping. It did some tricks with feedback and stuff. This product is also going to do those tricks, but this one has one more trick. And that trick is the extra JFET in this circuit. And it provides a Cascode type of situation between these 2 JFETs. The JFET on the top is chosen to have a much larger voltage, on voltage, or I should say pinch-off voltage. That's the correct term. It has a larger pinch-off voltage. And so it sets up a wider voltage range than the FET on the bottom. And the way it's wired up here, it creates a fixed voltage basically above the original JFET. And so it keeps that node, the drain node of the bottom JFET, from moving in voltage space. It keeps it fixed. So once again, it tries to minimize any changes on that FET. You want to keep that FET from not having any changes, which reduces the input capacitance and reduces the input impedance. Not so much impedance, but the input capacitance. A trick to get rid of what's called the Miller effect. This is it took me a while to figure out what the heck this was what this was doing. I did find the circuit in Horowitz and Hill, and so if you want to read more about this, you can find it there. So we end up with a JFET transistor that modulates current. It's configured in a Cascode configuration with 2 FETs. That modulating current then modulates the base current of the PNP transistor, which then drives the output section. Okay, almost done. So we need to put a bias on the JFET so that the gate is negatively biased with respect to the source. And that's done with a voltage splitter, and that's run over to the 1 gig ohm resistor that feeds the gate. This is just a fixed bias, and it's probably laser trimmed to match the part. And then there's also the negative feedback to the source, same as the Rhodes circuit. So the two circuits are similar. There's a few clever differences, I believe, in the Neumann amplifier circuit. And certainly the construction is way better and way more expensive than the Rhodes circuit. And so there's my comparison between these two microphones.